Welcome back. In this last section in Chapter 8, we'll be talking about inverse trigonometric functions. Remember that a trig function like sine would take an angle theta as its input, and then as its output, depending on how we wanted to think about it, it would either be a ratio of the opposite side to the hypotenuse, or it could be that we had that sine of theta would take theta in as its input and give out y over r if we're thinking about that definition of our trig functions. Either way, what we would like to do is come up with the inverse of a trig function, where we'll take instead as the input that ratio of opposite over hypotenuse, or y over r, and give as the output the angle. Now, there's one big problem here, and this is the big problem right at the start, which is that it's only one-to-one functions that are able to have inverses. And if you're thinking back to 8.1, the graphs of sine and cosine, sine for sure is not a one-to-one function, because even if I draw only one full cycle of sine, you can see already that a horizontal line will pass through the graph of sine in more than one place, making it not one-to-one. And the same thing would be true of any other trig functions that you might be interested in. So, for example, sine is not one-to-one, and cosine is also not one-to-one. But if you're thinking about tangent, also not a one-to-one function, because if you did more than one period of it, so let's say we drew two full cycles of tangent, then there we go. We've got a vertical line crossing through our graph in two different places. Now there is a workaround here, which is, although sine and cosine and tangent and all the other trig functions are not one-to-one if you use the entire domain, if you restrict the domain, then they would be one-to-one functions. So, for example, if you were thinking about tangent, you might say, well, I'll just restrict myself to one full cycle, from negative pi over 2 to pi over 2, and then you would have a one-to-one function. Or if you're thinking about sine and cosine again, you would need to restrict it to just a smaller part of the domain where it would be one-to-one. So the idea here is that we're going to take our graph of our sine function, and if we wanted to restrict it to something that's one-to-one, we could just look at sine on the interval from negative pi over 2 to positive pi over 2. Because we know what the graph would look like. That from 0 to pi over 2, we're going from 0 up to 1, and from 0 down to negative pi over 2, we're going from a y value down to negative 1. And this, for sure, would be a one-to-one function. So here, any horizontal line I feel like drawing passes through this graph in exactly one place. So therefore, yes, we do have something that is a one-to-one function. So we're thinking about it now as taking sine and restricting it to this domain from negative pi over 2 to pi over 2. Then you would have a one-to-one function, and then you could define the inverse of sine. And we define the inverse of sine as being sine inverse of x. So that notation, it's similar to the notation that we had for f inverse, the little -1 here, not an exponent. It's meaning the inverse of our, in this case, sine function. Some other books will use, instead of sine inverse with a little -1, they'll call it arcsine and write it as this. And that's another way, and these are both equivalent to each other, that when we say sine inverse of x, we are also saying arcsine of x. The reason why, just in case you're curious why it's being called arcsine, remember that we're talking about, in this case, our angles being measured in terms of radians. And remember that the way that we defined a radian was that for a unit circle, the angle theta, that radian measurement was the same thing as the distance of that little arc that we have there. That's why it's called arcsine, because when it's giving you an angle theta measured in radians, it's also, in a sense, giving you the length of that arc length. So both of these are equivalent, and so you may see me sometimes using sine inverse, you may sometimes see me writing arc sine, but that would be true, that they would be exactly the same function. One other thing that I just want to be careful about here is when I say the domain is from negative pi over 2 to pi over 2, that is the domain that we're working with. There are other ways that you could have defined your trig function sine to restrict its domain. So maybe I might have decided to restrict my domain from pi over 2 to 3 pi over 2, in which case I would have just that part of the sine function. And again, that would have been one-to-one. It just would have been a different choice. So do be aware, because for some of the inverse trig functions, some books will choose different restricted domains. This is fairly standard, though, for sine inverse, that we would be thinking about restricting the domain for sine to being from negative pi over 2 to pi over 2. The other part here, when I say negative pi over 2 to pi over 2, I do mean that quite literally. So although you might be thinking, for example, about something like this that has a reference angle of 45 degrees, you might be thinking about that as being 315 degrees or 7 pi over 4. But that would not be something that's inside that domain. If you really wanted to think about that angle, you would have to think about it as being negative pi over 4, so that it would be something within that domain. So the idea again is that when we're talking about inverses, it's exchanging the inputs and the outputs. So for sine of x, if you gave it an input of pi over 6 or 30 degrees, it gives you an output of 1/2. So that means for sine inverse, it would do the reverse. Instead of pi over 6 being the input and 1/2 being the output, you would have 1/2 being the input and pi over 6 being the output. Again, another example here, for sine pi over 4, 45 degrees, sine of that is root 2 over 2. So then for sine inverse, it would exchange the two. The input would be root 2 over 2, and the output would be pi over 4. One little caution that I want to give here for this, not this particular problem, but for everything that we're doing with inverse trig functions, that the angles are always going to be measured in radians. So although I'm going to be occasionally saying things like referring to this as being a 45-degree angle, that's just for the convenience for your understanding. But for writing, because we're talking about our trig functions as being defined where the angle is measured in radians, then I'm expecting for the inverse trig functions the same thing to be true. The angle's measured in radians again. So when we're doing any of this work with inverse trig functions, or also, as you might have noticed when we were graphing our trig functions, we were always using radian measurements. And so that's what we'll be doing here as well. So things, of course, that we can imagine out of this, we know, for example, this sine function has a couple of nice points. You've got the point pi over 2 comma 1, and you've got the point negative pi over 2 comma negative 1. So that means that for sine inverse, it should exchange those inputs and outputs. You should have the point 1 comma pi over 2, and you should have the point negative 1 comma negative pi over 2. And that's exactly what these 2 points are right here. We have the point negative 1 negative pi over 2, and the other coordinate that we have over here, that is the point 1 comma pi over 2. So again, just like any other graph that we're doing that has an inverse, we are just switching the inputs and the outputs. So if we know the points that are on our graph, then we know the points that are on the inverse function. Also to note here that for our trig function and the inverse trig function, as usual, it's switching the domain and the range. So for sine here, we had our domain restricted from negative pi over 2 to pi over 2. And so for inverse sine, the range was from negative pi over 2 to pi over 2. For sine, the range was from negative 1 to 1. And that means for inverse sine, the domain is from negative 1 to 1. Now, for most of the nice values of our trig functions, the ones that we saw that were values that corresponded to our usual angles, 30, 45, 60, 90, and multiples of them, we can use those special triangles just as we did before to find values for inverse trig functions. And of course, the way that this will work will be easiest if you're really good at already calculating your trig functions. So for example, for me, if I know which angle it is that sine of an angle gives me a half, and since I know what that angle is, then I should know what would be the value for sine inverse of a half. It would be whatever that angle is. Of course, if you don't know what the angle is that gives you sine of a half, sine of that angle giving you a half, you can figure that out by drawing yourself your special triangles. So here, when I'm drawing my special triangles, I'm going to be writing my angles in radians, but I'll say them at least in degrees. So we could have 30 degrees, which is pi over 6 radians, or we could have 60 degrees, which is pi over 3 radians, and our side lengths would be 1, root 3, and 2. So one thing that we can see here would be if you were thinking about the angle pi over 6, sine of pi over 6 would be opposite over hypotenuse, or a half. So we know that sine of pi over 6 is a half, and so that means sine inverse of a half should be pi over 6. In addition to the special triangles, don't forget that we also had sine evaluated at 0, 90, 180, and so on, using the fact that for any angle theta, sine of theta would be the y-coordinate when we're talking about the unit circle. And if you're thinking about where does sine have a value of -1, well, that happens down here. The y value would be -1 when we're talking about 270 degrees, or in this case, -90. So I could say that I know that sine of -90, negative pi over 2, is -1. So sine inverse of -1 should be negative pi over 2. For the next one, arc sine, or sine inverse of negative root 3 over 2. I'm going to go back to my special triangle on the previous slide, because one thing that you might notice would be that this would also be the special triangle that we'd be using if we were thinking about looking for 3 pi over 2. If you're thinking about 60 degrees, or pi over 3, sine of 60 degrees would be root 3 over 2, which is close to what we want. I know that sine of 60 degrees is root 3 over 2, but then you also know if sine of pi over 3 gives you root 3 over 2, and you know that sine is positive in quadrant 1, positive in quadrant 2, but negative everywhere else, you know then that if you're thinking about negative pi over 3, it should have a value of sine of that being negative root 3 over 2. So arc sine of negative root 3 over 2, that's negative pi over 3, negative 60 degrees. Now, again, if you have to think in terms of degrees while you're doing your work, feel free. Just make sure that when you're giving your answer that the angles are being given in terms of radians, which is what I'm expecting. Now, this is where we can finally use these inverse trig functions that we have here. So you can see there's the inverse sine function, inverse cosine function, inverse tangent function. And all of those you would access by using the second function button. So if you wanted to find out what was the inverse sine of some number, you would enter in second function sine. That would give you sine inverse, and then you would put in whatever the number is that you're looking for. Now, One thing just to be clear, of course, remember that we want our output to be given in terms of radians. So you would have to check and make sure that this is not degrees. You would have to check and make sure that you are in radians mode, and you can change to radians mode by using the DRG button as we did before. So make sure that it's giving you an output. In this case, the output would be degrees if you didn't have it changed to radians. So change it to radians so that the output is radians. So for the most part, I'm not interested in finding approximate values unless I ask you, can you find an approximate value for inverse sine of something? In which case, go ahead and now use your calculator. So the fact that this question is telling me to give my answer rounded to 3 decimal places, that's what's telling me that I'm going to need to grab my calculator. So take my calculator, put it into radians mode, and then enter second function sine, and then you'll see in the little display window sine with a little -1, that's sine inverse. And then we just need to enter 7/10 and hit equals, and we'll get about 0.7753, and this of course is an angle measurement, and it's an angle measurement in terms of radians. Okay, so now we're going to talk about composing a trig function with its inverse. And this is something where we talked about this back in 3.7 when we first introduced the idea of inverse functions. We said that if you had x that was inside the domain of f of x, then f inverse composed with f would give you x back. And the same sort of thing, if x was in the domain of f inverse, then f composed with f inverse should give you x back again. And the reason, of course, behind that is just the idea of what does our trig function do when we compose it with an inverse. So if we're thinking about our sine of x, taking an x value and bringing it to our range, we'll get some sort of output. And then if we applied sine inverse, it should take us back to the start again. This is, of course, if we're taking an x that's inside the domain of f. And same thing is true for the other idea here, f composed with f inverse. If you're taking something in the domain of f inverse, and then the output will be some sort of an angle, and then if you take f of that angle, sine of that angle, it'll give you back your original value again. So as long as we're taking things within the domain of f or within the domain of f inverse, then these are really easy questions. So if x were in that restricted domain of -π/2 to π/2, then sine inverse composed with sine, they would just cancel each other out. You'd be left with just the value of x. Or if we were doing the reverse, taking something from -1 to 1, then sine composed with sine inverse would again just give you x. So here we've got sine inverse of 0.2. So again, what is the sine inverse of 0.2? We don't really need to know, because again, if you're thinking about what sine does, sine takes some sort of an angle and gives you as its output either opposites over hypotenuse or y over r, depending on how you want to think of it. That's what sine does. Sine goes in this direction. And sine inverse goes in the reverse direction. It takes some sort of ratio of opposite to hypotenuse or y over r and gives you an angle as your output. Here we're taking some value 0.2, and sine inverse will give us some angle, and I don't need to know what that angle is, because when I take sine of that angle, the answer is it will be 0.2. It'll bring me back to the start again. So sine of sine inverse of 0.2 is just 0.2. And the reason we know that is because 0.2 is something that's in the domain of sine inverse. Same thing with the next one. Sine of π/6 is in the inside. And I know if I did sine of π/6, that would give me, again, 1/2. That would be the ratio of opposite to hypotenuse. But then when I apply sine inverse of that, sine inverse of 1/2, that'll give me my original angle back again. So since pi over 6 was in that domain of sine, then sine inverse of sine, that they cancel each other out, and I'm left with just pi over 6. Now, of course, there's the obvious, which is if x were not in that restricted domain for sine inverse of -1 to 1, then sine inverse would be undefined. So for example, sine inverse of 2 is undefined, and that's because there's no angle where sine of theta is equal to 2. There's no answer to that. What is the angle where sine of theta is equal to 2? Which means sine inverse of 2, there's no angle that corresponds to it. Now, if we're thinking about something like sine composed with sine inverse, if sine inverse is undefined, then sine composed with sine inverse would also be undefined. So if we know that, for example, sine inverse of 2 does not exist, it's undefined, then neither does sine of sine inverse of 2, also would be undefined. Now, we don't have the same sort of thing showing up for the reverse when we're doing sine inverse composed with sine. Remember that when we took our function sine of x, we restricted the domain to being from -pi/2 to pi/2. However, you could still, of course, evaluate sine of x outside of that domain. I mean, there's nothing stopping you from finding out, for example, what is sine of pi, and you could calculate out that, yes, indeed, that is 0. But if you asked me now, well, what is sine inverse of 0, I'm not going to get pi back as my answer because pi is not one of the values in that restricted domain. So if I asked you, what's sine inverse of 0, what is the angle that gives you sine of 0, and that angle has to be in that restricted domain, well, the answer is the angle would be 0. So if you were looking for sine inverse of sine of pi, although sine of pi gives you 0, sine inverse of 0 doesn't give you pi back. Sine inverse of that would give us 0 as our answer. So instead of getting our original answer back, our original angle, we get an equivalent angle that's inside of our domain that gives us the same output value that sine of pi did. Sine of 0 and sine of pi are both equal to 0, and that's why it gave me 0 as the output rather than pi. 0 is something inside that restricted domain for sine, and it is something inside that restricted domain for sine that has the same output that pi does. So let's do some examples here. We're looking for sine of sine inverse of 1.3, and right away, this is the fast and easy one. We can just stop and say that sine inverse of 1.3 definitely is undefined. And that's because sine inverse's domain is only from -1 to 1. And since that's undefined, then the composition, sine composed with sine inverse, is also undefined. So the answer to part A is undefined, no answer. Now, if we're thinking about this next one, sine inverse of sine of 9 pi over 10. So if you're thinking about 9 pi over 10 for just a moment here, 9 pi over 10 would be in quadrant 2. That's where 9 pi over 10 is. And it has reference angle pi over 10. One thing that we know is that if we're thinking about sine, that sine is positive in quadrant 2. So when we ask ourselves, what is sine inverse of sine of 9 pi over 10, we're going to get an angle back as our answer, but it won't be 9 pi over 10. The reason it won't be 9 pi over 10 is that the restricted domain for sine is from -pi/2 to pi/2. So whatever I get as my answer for sine inverse, it's going to be an angle that's somewhere in either quadrant 1 between 0 and pi/2, or quadrant 4 between 0 and negative pi over 2. Now, this is the reason why I mentioned here whether sine was positive or negative. I know that I'm not going to be getting an angle in quadrant 4 because that would be an angle that would give sine a negative value. And I know sine of 9/10 pi should be a positive value. So that's letting me know that actually the angle that I'm going to be having as my output should be in a quadrant where sine is positive, and that would have to be then quadrant 1, where everybody is positive. The other thing, of course, that we know is that when you have two angles that have the same reference angle, in this case 9 pi over 10 and pi over 10, they both have the same reference angle of pi over 10. And so since sine is positive in quadrants 1 and quadrant 2, you know that sine of pi over 10 is equal to sine of 9 pi over 10. Whatever the actual value is, kind of irrelevant. We don't need to know what is sine of pi over 10 or sine of 9 pi over 10, but we do know that whatever the value happens to be, it's identical for both. So that means that sine inverse, it can't give you 9 pi over 10 as the output because 9 pi over 10 is not inside the domain. It will give you pi over 10 as the output because pi over 10 is inside the domain of sine, and it's the angle that gives you the same output that 9 pi over 10 would for sine. So that's the sort of workaround that we'll need to do if we're thinking about composing sine with sine inverse. So we'll have to ask ourselves, in this case, the angle was 9 pi over 10. What's the reference angle for that? And where else do we have that reference angle in our restricted domain that would give sine the same output as 9 pi over 10? So we said because sine is positive in both quadrants 1 and 2, and since 9 pi over 10 was in quadrant 2, then the other angle that we'd be interested in or thinking about would be in quadrant 1, and it would have to have the same reference angle of pi over 10, which meant that sine of pi over 10 and sine of 9 pi over 10, those were both equal to each other. So sine inverse would give me as its output pi over 10, the angle that gives you the same value as sine of 9 pi over 10, but with an angle that happens to be in that restricted domain from negative pi over 2 to pi over 2. Let's do one more here. So again, we've got an angle, 15 pi over 13. And if I were thinking about where 15 pi over 13 is, remember, of course, that this is pi, which you could think of as 13 pi over 13 if you wanted to. So 15 pi over 13 should be a little bit past that. And so the reference angle then should be 2 pi over 13. Okay, so we know where the angle is that we're looking for. Our angle happens to be in quadrant 3. And in quadrant 3, sine is negative. So we have to ask ourselves, where is it that sine is also negative in my restricted domain? Remember that my restricted domain for sine is negative pi over 2 to pi over 2. So in quadrants 1 or 4. I know quadrant 1 is where sine is positive, and quadrant 4 is where sine is negative. And so since I know sine of 15 pi over 13 is negative, then the angle that I'll be looking at, the equivalent angle, the one that's going to give me the same value for sine, would be negative 2 pi over 13. I know then that sine of negative 2 pi over 13 should have the same output as sine of positive 15 pi over 13. The reason I know that is because both 15 pi over 13 and negative 2 pi over 13, they both have the same reference angle, 2 pi over 13, and that they're both in quadrants where sine happens to be negative. So since we now know, since sine of 15 pi over 13 gives you the same value that sine of negative 2 pi over 13 would, then that means that sine inverse should give me negative 2 pi over 13 as my output. And that's because sine inverse only gives outputs from negative pi over 2 to pi over 2. That's why it's not going to give me 15 pi over 13 as an output. Again, 15 pi over 13 is not in the range of sine inverse because it's not in that restricted domain for sine.